In April of 2028, the aerospace firm X Labs is scheduled to launch a spacecraft with a singular target. The target is the near-Earth asteroid Apophis. Intercept physics require the spacecraft to catch it when it passes within 32,000 kilometers of Earth. As Apophis dips below commercial satellite altitude, the one-way spacecraft will deploy payloads to map its internal structure. This structural mapping is a required precursor for a distinctly different industry. Asteroids like Apophis contain massive concentrations of rare earth metals, materials like platinum, cobalt, and gallium. We currently extract these materials from terrestrial mines to power global electronics. The long-term objective of this mission profile is to reverse that supply chain, sourcing the raw materials for terrestrial hardware directly from the solar system. Extracting resources from orbit is a strict systems engineering challenge, gated by a highly constrained intersection of orbital physics, unit economics, and localized manufacturing. Historically, deep space exploration relied on massive, unrecoverable capital expenditures funded by governments. Commercial asteroid mining operates under a different constraint. It must be profitable. To achieve that profitability, a private firm has to solve three operational domains simultaneously. First, they need a physical architecture capable of executing extraction autonomously, far beyond the reach of real-time communication. Second, they must run rigorous techno-economic modeling to guarantee the mission's net present value, or NPV, remains mathematically positive. Third, they need to aggressively drive down the production costs of the hardware itself by operating within highly localized manufacturing ecosystems. Right now, those three domains are converging in Long Beach, California, an area increasingly referred to as Space Beach by the companies clustering there. If a private firm expects to survive the deep space economy, they have to master all three of these domains at once. Physical architecture is dictated by distance. Operating 100 million kilometers from Earth causes a strict delay in light speed communication. That latency makes direct remote control impossible. The spacecraft must execute extraction logic on its own, relying entirely on onboard edge compute autonomy. Traditional monolithic spacecraft designs, single, massive machines, concentrate too much risk for this environment. If one component fails during a complex volatile extraction, the entire mission is lost. The leading theoretical solution avoids that risk by breaking the monolithic spacecraft into a distributed swarm of small, highly specialized CubeSats. Methodical. This swarm executes the extraction in sequential phases. First, specific units deploy to physically de-spin the asteroid, stabilizing the target surface. Once stabilized, laser-equipped spacecraft heat the regolith. As the material off-gases, a separate group of capture craft maneuver in to trap and condense those volatiles for transport. Finally, to move the payload back toward lunar orbit without burning through limited fuel reserves, the return vehicles deploy propellantless electric sails. This swarm architecture bypasses the operational limits of deep space, but it introduces a new demand. It requires an aerospace company to manufacture spacecraft in massive, continuous volumes. Advanced extraction physics are irrelevant if the mission results in a net financial loss. To determine viability, analysts use a foundational equation: profit equals revenue minus cost. This chart models the profit threshold for water mining. The mission's profitability shifts entirely depending on whether the hardware is expendable, or as shown in the data points for to reuse, capable of flying multiple times. But the variable that dictates profitability more than anything else is the extraction throughput rate, the physical mass of material the equipment can process per second relative to its own dry weight. By utilizing the swarm architecture and producing identical CubeSats in high volumes, engineers can exploit the aerospace learning curve. Production costs systematically drop with every consecutive unit built. Water is relatively easy to extract. Platinum is not. Because the ratio of platinum to raw asteroid material is so low, achieving the same financial break-even point requires the equipment to process the regolith at an exponentially higher throughput rate. Even if that extraction rate is met, the firm faces the price elasticity of demand. If a company returns massive quantities of platinum to Earth, they flood an inelastic market. The price per kilogram drops, and the mission's net present value collapses with it. To maintain the market price, the mining firm has to strictly throttle how much material they inject into the global supply, pacing it carefully against the natural reduction of terrestrial mining outputs. Securing a positive return requires a delicate mathematical balance, maximizing the volume of spacecraft manufactured to lower costs, while strictly limiting the volume of resources brought back to the physical market. Executing the required learning curve cost reductions demands a physical aerospace supply chain that prioritizes rapid iteration over massive scale. Instead of relying on massive footprints and rigid tooling, commercial firms are shifting to the lean, highly iterative pipelines of modern additive manufacturing. By clustering these facilities in close geographic proximity, companies can strip out the overhead costs associated with logistics. This is the exact ecosystem functioning in Long Beach today. A critical node in this network is California State University, Long Beach. The academic institution operates as a direct R&D incubator and a dedicated talent feeder for the private ventures located just down the street. Inside the campus labs, engineering teams test new manufacturing techniques, like integrating nanoparticles into metal 3D printing to reinforce rocket structures. In the solid propulsion labs, researchers use holographic measurements to track microscopic particle motion, allowing them to rapidly formulate and integrate high-energy density materials. They build custom pressure-fed static fire test stands and transport them to the Mojave Desert, safely subjecting their 3D printed thrust chambers to 2,000 pounds of thrust force. When firms like X Labs or Relativity Space hire graduates straight out of these labs, they bypass the massive capital expenditure normally required to train engineers on complex additive systems. These hyper-localized university-to-industry clusters are the physical engines driving spacecraft-specific production costs down to the point where deep space extraction becomes economically viable. Commercial asteroid extraction relies entirely on the integration of this triad, deploying autonomous swarm physics, rigorously managing the NPV equation, and operating within localized 3D printing ecosystems. The initial hardware execution is only a few years away. When Apophis makes its closest approach in 2029, these autonomous craft will be positioned to map the terrain. The anticipated subsequent phase scales the architecture up, extracting the resources and towing the payloads back to commercial science parks stationed permanently in lunar orbit. The rare earth metals currently extracted from terrestrial soils are finite and diminishing. Just a few million miles away, the main asteroid belt holds an effectively infinite mineral reserve. With capital barriers falling and manufacturing pipelines optimized, the mathematical path to a space-based supply chain is now a matter of execution.